In the last lecture, we discussed about the concept of radiation. We discussed about how the radiation takes place, what are the various theories of radiation transport, and we also discussed about the electromagnetic spectrum. In today's lecture, we are going to discuss about the black body concept. So what is a black body? A black body is defined as a body which is perfect emitter and absorber of the radiation. So basically it will emit the maximum amount of the energy and it will absorb the all amount of the energy which is falling on it. It has the following properties. It's an ideal surface and it has the following properties. Number one, a black body absorbs all incident radiation from all directions at all wavelengths. So whatever may be the direction, whatever may be the wavelength from which the radiations are coming, it's going to absorb all of those. At a specified temperature and wavelength, no other body can emit energy more than a black body. So that means the black body is going to emit the maximum amount of energy. Although the radiation emitted by a black body depends upon wavelength and temperature, it is independent of direction. That is, it is diffuse in nature. So it means when it will be emitting the energy in different directions like this, and then this, the intensity of the radiation will be same in all the directions. A black body neither reflects nor transmits any amount of the incident radiation. However, in actual, no surface has all the properties mentioned above for a black body. The term black is different from visual observations. Now let us try to see what is the meaning of this particular sentence. A surface coated with lamp black appears to be black in color to the human eye in the visible range of spectrum, but turns out to be black for thermal radiation also. So that means if there is a lamp black, it will be visually also it's black in color, as well as it will be black for the thermal radiation also. That means it's going to emit the maximum amount of the energy. So it can be considered as a black body. On the other hand, ice and snow appear quite bright to human eye, but are almost black to thermal radiation at all wavelengths from lambda is equal to 0 to lambda is equal to infinity. So at all wavelengths, the ice will be working as a black body. However, it is not black in color. So that is what you need to understand, that it is not necessary that whether a body is black or not, but black here means it is emitting the maximum amount of the energy and absorbing all energy which is falling on it. Now we can take a case of a cavity as a black body. Now you can see a cavity here. So consider a radiation beam which is entering the cavity of an enclosure as shown in figure. So what we have considered here is there is a very small hole here through which the radiation beam is entering into this cavity. So it experiences many reflections within the enclosure and almost entire beam is absorbed by the cavity and the black body behavior is experienced. So what does this mean? So when the radiation beam is entering here, so it falls here first of all. Then this is the first reflection and partial absorption here. So reflection is taking place and the remaining energy is falling at this particular location. Then this is the second reflection and partial absorption. Then once again, it is falling here. This is the third reflection and partial absorption. Similarly, this is the fourth reflection and partial absorption. And then this is the fifth one. And once again, it may be like this. And a point will come when whole of the energy which is entering this small hole here, that would be totally absorbed by this cavity. So basically a cavity will behave as a black body. Now let us talk about the spectral and total emissive power. So this is we are now not talking about the black body. It is the spectral and total emissive power. Spectral emissive power is represented by E lambda and total emissive power is represented by capital E. All surfaces at temperatures above absolute zero temperature emit energy in all directions over a wide range of wavelength. So every body which you see around yourself, that is emitting energy in all directions and in a wide range of the wavelength. The energy emitted by a body will be going in all directions, and it may be in a range of wavelength, means it is not necessary the wavelength will be constant. So it may emit in a particular range of the wavelengths. Okay, that will depend upon the temperature as well as the uh, characteristics of the surface. Now, what is the total emissive power E? At a given temperature, the total amount of heat energy emitted by a surface in all directions means if you are considering a particular surface, what is the meaning of the all direction means? If we consider a hemisphere over this particular surface, then we will say it is all directions. And over the entire wavelength means lambda is equal to 0 to infinity. Per unit area, per unit time is called the emissive power. So just try to read it once again. At a given temperature, the total amount of the heat energy, so heat energy emitted, so what will be the unit of it? It will be joules by a surface in all directions over the entire wavelength per unit area means joule per meter square per unit time divided by time also. So it becomes watt per meter square. So that is the energy basically emitted per unit area in all directions and over entire wavelength is known as the emissive power. The emissive power depends on characteristics and temperature of the surface. It is designated as E and is measured in watt per meter square. And E is a function of emissivity epsilon, lambda which is wavelength, and T is temperature. So it is once again repeated here. Epsilon is the emissivity and it is a surface characteristic. Lambda is the wavelength of the radiation and its unit could be micrometer or could be meter. It depends which unit we are using actually. And T is the absolute temperature of the surface in Kelvin. The amount of radiation energy emitted from a surface at a given temperature T also varies with wavelength lambda. In the previous case, when we talked about the total emissive power, we have considered the radiation energy emitted over the all wavelength in all the directions. So if we focus our attention on a particular value of the lambda, then that value of the energy emitted by the surface in a particular wavelength, in a particular range of wavelength d lambda around lambda will be known as the spectral or monochromatic emissive power. Spectral or monochromatic relates to the wavelength of the energy emission. So spectral or monochromatic emissive power E lambda is defined as amount of radiation energy emitted by a surface. So it means joules at an absolute temperature T per unit time. So divided by second, per unit surface area means divided by meter square, and per unit wavelength d lambda around the about the wavelength lambda. So you have to take micrometer also. So what will be the SI unit of E lambda? It is watt per meter square per micrometer. And sometimes you can see that it can also be written as watt per meter square dot meter. When we are taking the wavelength in meter, then the unit of spectral or monochromatic emissive power will be watt per meter cube. But in most common case, we take it as watt per meter square per micrometer because we are taking the wavelength in microns or micrometer. Now, spectral or monochromatic emissive power E lambda, that is what we are talking about. We have now from it, suppose we have to calculate the total value of the emission or total emissive power from the spectral emissive power. So we have to refer to this particular graph, which is shown here in figure 12.4. So you can see here, the radiation is emitted over the entire wavelength range varying from lambda is equal to 0 to lambda is equal to infinity. And you can see this curve. This curve is showing the emission in over the whole wavelength range from varying between lambda is equal to 0 to lambda is equal to infinity. So as you can see here, this is the curve here. Now the emissive power of a surface over the wavelength ranges from lambda to lambda plus d lambda, and it is given by this value dE is equal to E lambda into d lambda. So if what we have done here in the curve is we have considered this hashed area, okay, and what you can see here is this energy, total energy is given as dE, and if we take this E lambda as the average value for this curve, for this much d lambda range, then what will be the total energy? It can be considered as a rectangle here. You can see it here. It's a rectangle. So this range is d lambda. This is the wavelength range d lambda, and this is the value E lambda. So total energy emitted will be equal to dE, which will be equal to E lambda into d lambda. Basically, it's a area of the rectangle. And if we have to calculate for the total wavelength range from lambda is equal to 0 to lambda is equal to infinity, then we can integrate this particular equation E lambda d lambda over the total wavelength range from lambda varying from 0 to lambda equal to infinity. So that is what you can see it here. What is dE? D is the emissive power in a given wavelength band between lambda to lambda plus d lambda, and its value is in watts per meter square. What is E lambda? It is the monochromatic emissive power, which is in watt per meter square micrometer, which has been considered here while calculating the total emissive power. And the total emissive power of the surface over the entire spectrum of wavelength varying between lambda is equal to 0 to infinity is given as E is equal to E lambda d lambda with integration from 0 to infinity. And this way we can calculate the total emissive power. Here E is the total emissive power. Now, what is irradiation? Irradiation is, now this is a different concept. Now, first of all, you see this particular figure. And before, okay, first of all, we can read this definition so that you understand it in a better manner. The irradiation is the total radiation energy incident per unit area, per unit time over the entire wavelength from all directions. So you can see we are talking about the energy which is falling over the surface from all entire wavelength range, which is varying from lambda is equal to 0 to lambda is equal to infinity from all the directions. Means this is coming from the hemisphere. So we can consider that the energy is coming over the surface from all the directions. And it is a total radiation energy. Total radiation energy means joules. Incident per unit area means meter square from all the directions over per unit time. So divided by second. So it would be watt per meter square. So it is basically the incident radiation which is shown here. And it is coming from all the directions and for all the entire wavelength range lambda equal to 0 to infinity. Now when it falls over this particular surface, a part of it will be absorbed. And this absorbed part is given by given the name alpha into G, or when I say it can also be written as G times alpha. Means G is the total incident radiation, a part of which is absorbed here is known as G infinity, G alpha, which the part which is reflected, it is given the name G rho. It is given by rho times G, and the part which is transmitted is given by the formula tau into G, and it can also be written as G tau. And it is a semi-transparent material. That means it will absorb certain amount of the energy, transmit certain amount of the energy, and it will also reflect. So for most of the surfaces, when the radiation incidents on a body, part of it is absorbed, part of it is reflected, and remaining part is transmitted as shown in diagram. Now, what is the total or average or hemispherical absorptivity alpha? So we are talking about the absorption rate, which is actually absorption over the all wavelength and all means of the energy coming from the all directions and over the all wavelength range. So that is given the name as alpha. Means it is total or average or hemispherical absorptivity. It is not dependent upon either wavelength or direction. It is a total in nature. So a black body absorbs all incident radiation, hence its absorptivity is considered as unity. But real surfaces do not absorb all energy incident on it. And then we define total or average or hemispherical absorptivity of that particular surface, and it is defined as fraction of the radiation energy incident on the surface from all directions over entire wavelength spectrum from lambda is equal to 0 to infinity, that is absorbed by the surface. So the energy which is absorbed by the surface is given the name G alpha. Okay, so this is alpha is given by G alpha. This is the absorbed amount of energy, and G is the total amount of the incident energy. So the ratio of these two is known as the total or average or hemispherical absorptivity. Similarly, we can define the reflectivity. Once again, it is, though I have written it as reflectivity, it is basically average or total or hemispherical reflectivity. Means it is reflecting the energy which is falling over it in all directions or all wavelength. So when a radiation is incident on a non-black surface, a fraction is always reflected by the surface. The reflectivity of a surface is defined as the fraction of radiation energy incident on a surface from all directions over the entire wavelength spectrum from lambda to 0 that is reflected by the surface. So that means this part, we are talking about this part, and it is given the name G times rho. So what is rho? Rho is reflectivity in all directions over the all wavelength range, and it is equal to the ratio of G rho divided by G. And what is G rho? G rho is the energy reflected by the surface. So now I am going to talk about specular and diffuse reflection. Because in the previous case, we are considering the energy is reflected in all directions. When I say energy is reflected in all directions, it means it's a sort of diffuse reflection actually. If a surface is perfectly smooth and the angle theta of incident and reflected rays is equal, then the reflection is called specular or mirror-like reflection. So you can see this particular diagram. This is the incident ray. It is coming at an angle theta, and it is also reflected at an angle theta. So this is a specular or mirror-like reflection of the incoming ray, and this is the normal about which the incident ray is making an angle theta. Similarly, we can have the diffuse reflection. What is diffuse reflection? If the surface has some roughness, the incident radiation is scattered in all directions after reflection. Such reflection is called diffuse reflection. So you can see this is the incident ray. It is coming at an angle theta. Once it falls back at this particular point, it is reflected in all directions, here, 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 and so on. So the reflection is taking place in all directions. So such reflection is known as diffuse reflection. However, there can be some real surfaces which are neither specular or nor diffuse, but the combination of diffuse and specular behavior. So that is shown here. You can see here, this is the incident ray which is coming at an angle theta, but when it is reflected, it is going in a some of the particular direction, but not in the all directions. So you can see here, these are the reflected rays. So this reflection is between the diffuse and the specular reflection, and it is considered as a real surface. And it is because of the roughness of the surface that the reflection may not be going in the all directions, or it may be due to some other reasons. Now, what is transmissivity? Or we can also call it as the total or hemispherical or average transmissivity, and it is represented by tau. So you can see it. Once it's a semi-transparent material, a part of the energy of incident radiation G, that is, what is incident radiation? It is known as irradiation. Okay, so incident radiation which are falling on a surface is known as the incident irradiation, and a part of it which is transmitted is actually represented as G tau, and the ratio of G tau to G is actually known as the transmissivity. So you can see here, what is tau? Tau is the fraction of the incident energy transmitted through the surface, and it is given by tau is equal to g tau by g, where g tau is the energy transmitted by the surface. And when we consider all these reflection, absorption, and transmission for a surface, then the sum of absorbed, reflected, and transmitted radiation energy is equal to the radiation energy incident on the surface. What is incident on the surface? It is G, and it is consumed like this part is absorbed, this is reflected, and this is transmitted. And if we divide the whole equation by G here, what we are going to get here? This will be 1, and this value will be equal to alpha. The second one value will be equal to rho. The third value will be equal to tau, and the total will be equal to 1. That means the sum of reflection, absorption, and transmission can never be more than 100%. So that is what I wanted to discuss in this particular lecture. The remaining concepts we will discuss in the next lecture.